Okay, so it's week 4, and I'm just in the Moodle shell here, and I thought we'd do a little bit today is talk about Stirling engine theory. And I think probably one of the best ways to look at this is a couple different animations. And I know Wikipedia used to have them out there, much easier. Take a look at this. And Stirling engine is something that can be run from a thermal gradient. So you've got a hot side, obviously, which would come from the sun or some other source. But the point is, you can make a hot side without setting something on fire, and that's the whole point of the solar thermal. And then you've got a cold reservoir. So just in the same way that a internal combustion engine works with hot gases inside and cold gases toward the outside, a Stirling engine works in a similar fashion, not quite, and we'll look at the subtle differences here. And there are 2-cylinder Stirling engines as well as 1 cylinder. So let's just take a look at this first one here. Reverend Robert Stirling of Scotland, very simple, often billed as a safe alternative to steam. One thing worth noting is since you're not necessarily making steam, the pressures are lower and the temperature gradient is different, and therefore the efficiency is going to in general be a little bit less. So some success in industrial applications and small appliances, but was eclipsed when you had an electric motor, so electricity doing its thing. But if you have any heat, it can sort of be there, even with geothermal as mentioned. Okay, so what's going on? Obviously, for any engine to flow, any heat engine anyway, you're going to need some kind of heat source. So what's happening? I don't know if there's a way to kind of slow this guy down. But the important thing to note is that the molecules in this engine are actually flowing back and forth. So you can see, let's just take a look at the top first before we look at the bottom. So as this top cylinder expands, just keep an eye on it, you can see that the molecules, the particles, go from hot, so they're coming in hot as red. This radiator on the side is cooling them, and so they're going back out cool. Now, down here, you can see when the cool molecules come in, it's the heat that is expanding this piston. So heat's coming in here and being dissipated out there. It's also worth noting, let's see if we can, there's a way to pause this guy. Let's just pause it. It's also worth noting that these two sides are always 90 degrees out of phase. That's another key element of the Stirling engine. So let's get this. Let's get the notes going here a little bit. So Stirling engine. First of all, it is a heat engine. It's versatile. Meaning that we can get heat from combustion. Sorry, my handwriting's not going to be the best today. Solar thermal. Or geothermal. And so there's always going to be some kind of delta T. Hot side, cold side. The one we're looking at right now is a 2-cylinder. Let's just take one more look, and obviously this guy has a heat source side that's being heated down here at the bottom, and then a heat. I wouldn't call it exhaust. There's really no exhaust here. I'll write that down too. No. So all of the working fluid stays inside, and it's just sort of, sloshing back and forth, if you will. You'll also notice that the two cylinders are 90 degrees out of phase. So I'll just read through this again, so my handwriting's really suffering. So it's a heat engine, number one. There is a delta T, so there's a hot side and a cold side. It's versatile. You could have, it's versatile in that you can run it with combustion, solar thermal, or geothermal. There is a two-cylinder style. I've just noted that there's no exhaust and that the two sides are 90 degrees out of phase. So we just kind of play that again. You can see this side is essentially at 180. This side is at 270. Play it some more. Now this side is at 90. Well, the flywheel itself is at 90, with this guy being at a I'll just call it a 45-degree angle, and this being a 90-degree angle. Click through again. So each one. So when this guy is at on the downstroke, the other one's sort of in neutral. There's a good shot right there. So this one's at the bottom of its stroke, and this one's mid-stroke. Right there, that's completed its stroke. The cold side is at mid-stroke, etc., etc. So that's what I mean by 90 degrees out of phase. Okay, so let's just see. There's also a single cylinder Stirling engine. Take a look at this guy, a little animation.
Introducing Dunkin's
nice thing about it too is
cold brew coffee, steeped slowly in cold water for small batches.
It's perfect.
Hi guys, welcome to howmachineworks.com. Today, with the help of this animation, let's learn how a Stirling engine exactly works.
Yeah, let's
so,
look at this one here. This one's a little better.
All right, son?
Okay.
Turn this up a little bit here. So there's the alpha that we just looked at, the two-cylinder. Here's the beta. We'll also take a look at the gamma. So again, here's that working fluid, and so the other thing to mention is that this flywheel continues to spin, and that's where your work is done, and that's why it's an engine. There's that 90 degrees I just mentioned. Check out the air here. So obviously this is the expansion. Okay, here we go. So the red side is getting hotter and hotter and hotter. It's expanding. As it does, it sucks that molecule down. Now as the cold side is expanding, that molecule is sucked back up. So the flywheel is missing, but it's actually continues to move it. And that's what's transferring or pushing the air. Hey, Shonamans. Just in time. Just looking at Stirling Engine, yeah. So that's the so-called alpha style. You know, in some ways, it's the sort of easiest to understand, if you will, because this side's got the side's sort of always hot, and this side is always cold. The other thing I just mentioned is that instead of an internal combustion engine, all the working fluid stays inside. And there's the flywheel put back in place. So we also talked about this could be a geothermal source, and the other side could be, out in the cold air. This is a little more difficult to understand in some ways. But you still have a hot side, there's your cold side. And there we go, just a single cylinder. And hopefully they'll open it up for us here in a little bit. There we go. So this one's being called the power piston, and you can see that the power piston is a little larger. The displacer is a little bit smaller because the gas actually has to pass back and forth past it. You can still see there's cooling fans are still right here, so you've got hot on that side, cold on that side. So there's this center shaft that passes through the power cylinder all the way to the displacer. This is kind of the key part. As the air cools, as the air on this side cools, it sucks the two pistons towards each other, and that's essentially where they end up there. So now that the air is cool, gets sent down to this side. You could think of these molecules as still like roughly blue because they're still heading towards the left. But once they hit that hot end, they're even hotter, forcing them back the other way. Again, it's not shown here, but you would then have this hooked up to some type of machinery. And in general, this is not going to be super efficient for transportation. unless, you somehow had something really cold inside your car and just everything on the outside was hot. This is the most interesting thing. You can still see that 90 degrees, 90 degree out of phase there that we just saw in the Alpha style. And when they say 90 degrees ahead, so the central one is the displacer, and it is 90 degrees sort of ahead of the power. We tried to build one of these a few years ago for the practicum, and it's a challenge. Yeah, it's a real challenge. What's that? Oh, really? Yeah, we tried to do it in 2 weeks from scratch. It was a little beyond the pale. Yeah. Yeah. So this one, I've actually have one of these in my office, so I can go grab it here during the break. You can run it on a cup of coffee. You can run it on a glass of ice. Not very powerful, but it works. So again, low temperature, and again just and so there's still a cylinder. See that cylinder in the middle? And there's a piston. Really just a single cylinder, single piston. Yeah, this is the one I have in my office. So you still have that displacer rod, not really displacer piston there. You're going to run this vertically, vertical axis, yeah. Oh, well, you know what? The one I have in my office it's a membrane on top rather than that piston, but you still have that, in a way I misspoke, because the one I have in my office, this is a membrane rather than that second smaller piston. Degrees C, so 4 degree, 3 or 4 degrees Kelvin. Mine were never quite. Mine were never quite that. They couldn't quite run with that small of a gradient. So again, the top is hot, the top is cold, the bottom is hot. And this is where we had trouble building it, is it's got to be loose, but not too loose. It actually has to be able to push. If it were super small, like if this guy were super small, it wouldn't really actually move air, it would just sort of flop back and forth around. Yes, yes you could. So you will notice that at some points the flywheel seems to be acting against the motor itself, which is true, but it's necessary to keep it moving. So as I said right there, the flywheel forces it through, and the cycle can continue. And again, that same 90 degrees is right there. 90 degrees out of phase. Nice and shiny. So yeah, you might, at this point, it's worth noting that the power, so the energy density of this is relatively low, but you can also notice that it's sustainable and that you're not burning the earth battery. Okay, I'm going to take let me wrap up my notes here. 90 degrees out of phase. The two-cylinder, that's the alpha that we saw first, and then the one-cylinder, you've got the beta, and then so in the beta, as we saw, the displacer shaft passes through the power piston, and then the gamma had that second, that second power cylinder on the top. One cylinder. Okay, I'll just take a little break here. We're almost at 30 minutes. I'll be right back.